So, come to this diagram again. So, this is actually the steady state error minus 0.0235 hertz, right. So, if you do the simulation, it will be coming like this is for non-reheat turbine. Non-reheat turbine, I told you that in the case of non-reheat turbine, right, then your then this your what you call from this block diagram, right, you drop this term, only one time constant will be there, you drop this term, just hold on, right. From for non-reheat turbine, this term should be dropped, I mean this term should be not, in that case K r is equal to 1. So, it will be this, that means this term will not exist. So, only this term will exist, in that case it will be your what you call state, the A matrix will be 3 into 3, this term should not be there. So, directly you join it, this term should not be there for non-reheat, that we have told you also earlier for non-reheat turbine. So, in that case the responses are like this, for reheat type the peak frequency deviation will be slightly higher, right, compared to your non-reheat type, but steady state error will remain same, right, because R and Kp values are same for both the cases, it will remain. Generation for your reheat type will take little bit more time to settle, it is uncontrolled mode. So, cannot be exactly 0.01, I told you it will be your what you call a little bit less, 0.0019 less, right. So, that is why your this is, and it will take slightly more time because you have reheat time constant 10 second is there, little bit slower. So, dynamic performance slightly slower than your non-reheat type, the black one is the non-reheat type, but ultimately it will not exactly 0.01. Through MATLAB Simulink also you can check that it is not 0.01, slightly less whatever you have shown. So, this is uncontrolled mode, dynamic responses for uncontrolled mode, u is equal to 0, that is uncontrolled mode of operation. This is time, this side is time, this is time, right, and this is your, this side is frequency hertz, and this is generator power in per unit megawatt, right. So, that is your some ideas about the dynamic performances. I am not asking you to write code or anything, just for general thing. For this course, no question of writing code, right. For your own interest, you can verify in MATLAB, because I strongly believe that everyone knows MATLAB Simulink thing nowadays, right. Code also very easily can be written for such kind of system, but that is beyond the scope, and one can verify the result using writing code and MATLAB Simulink. You will find all the results are identical, right. So, next we take say one small example, right. Just you have to try to understand that this example. So, a system consists of 4 identical 400 MVA generating units, right, feeding a total load of 1016 megawatt, 1016 megawatt, right. The inertia constant H of each unit is 5 second, 5.0 second, and your this total load is this one 1000 megawatt, this is 400 MVA, 4 identical generators, and your the inertia constant is 5 second on 400 MVA base for each unit. The load changes by 1.5%. For a 1% change in frequency, when there is a sudden drop in load by 16 megawatt. So, initially a total load of 1016 megawatt, but there is a sudden drop of 16 megawatt. Then what you have to do is, you have to obtain the system block diagram with constant H and D expressed on 1600 MVA base, right. You have to obtain the system block diagram with constant H and D. Second thing is, determine the frequency deviation assuming that there is no speed governing system. If there is no speed governing system, means that delta Pg is equal to 0, you have to take, this should be in your mind, that whenever they say no speed governing action means delta Pg will be 0, right. So, if you look at this now solution, that how we will make it. So, for 4 units on 1600 MVA base, H equivalent actually will become 5 into 5 is the inertia constant, the H it is given, this H is given here 5 second, 5 into there are 4 units, 4 identical 400 MVA units. So, 4 in 400 into 4 and on 1600 MVA base, right. So, what we are doing is that we are because it is asked that you find out on 1600 MVA base. So, divided by the base MVA 1600. So, that is actually H equal becoming actually 5 second. So, same as whatever it is, the equivalent one is 5. Now, here frequency is not mentioned, right. Then you ask say in this case you have assumed f0 is equal to 50 hertz. So, now if F0 is equal to 50 Hz, D is equal to delta PL upon delta F. Now, it is given that it is 1.5, that load changes by 1.5% for a 1% change in frequency. So, now there and your what you call, there is a sudden drop in load by 16 megawatt. 16 megawatt means initially it was 1016, now it is 16 megawatt. So, load is now 1016 minus 16, so it is 1000 megawatt. That is why, and it is 1.5%, the load changes 1.5%, that means it will be 1.5 into 1016 minus your 16 divided by 1% change in frequency is 1 into 50. Percent will be cancelled. If you put it is 1% here, if 1.5% here, 1% of that, percent means 1 upon 100, here also 1 upon 100, here also 1 upon 100, 100 will be cancelled actually. So, that is why directly we are writing that 1.5 into 1016 minus 16 upon 1 into 50. So, if you simplify this and multiply all these things, they write it is coming actually 30 megawatt per hertz. It is in real unit, because this 30 megawatt and this is hertz. Now, D is equal to then your 30 megawatts per hertz, and base is mentioned here 1600 MVA. This is the base. That means, this numerator is 30 megawatt. You have to make it in per unit megawatt. So, divide this one by 1600. So, it will be 30 by 1600 per unit megawatt per hertz. That is your 3 by 160 per unit megawatt per hertz. So, D is equal to 3 by 160 per unit megawatt per hertz. I hope you have understood this, because it is a real unit. This is actually megawatt, this is actually megawatt, but base is 1600. So, we are dividing it by 1600. That means, this megawatt will be converted to per unit megawatt. So, this is the value, D is equal to 3 upon 160 per unit megawatt by hertz, but frequency anyway you are not changing to its per unit value. Frequency is its original value, original unit, that is hertz. Right. Therefore, we know this, we know that T p actually we know 2 H upon D F0 we know, but in this case we found actually H eq is equal to 5 seconds. That is why instead of H we are writing T p is equal to 2 H eq upon D into F0. So, 2 H eq we got 5 second, right, H eq is 5 second, but we know T p is equal to 2 H upon F d 0, but instead of H we put H eq, same thing, right. You put 5, H equal to 5 here, and divided by D, D we just got 3 by 160, and F0 is equal to 50 hertz. So, that is becoming 32 by 3 second, right. So, this is your time constant T p, and it is asked in the problem, it is asked that your what you call obtain the system block diagram with constant H and D. System block diagram in a no speed governing system, actually block diagram I have made it here, right, at least made it here. So, it is no speed governing system. So, that is why delta P is equal to 0. This is delta P L, the load disturbance, this is minus, this is plus, but it is 0. No speed governing action means that it is 0, right, delta P is 0, and this part you know K p upon 1 plus S T p, this is delta F. Only this part it is asked, not as a whole, all because the speed governing is not there. So, no need to draw the this side block diagram, you have to understood this, only this much, only this much. So, K p is equal to 1 upon D. So, D is equal to whatever we have got, right. So, it is 3 by 160. So, it is 160 by 3 hertz per megawatt, right, and T p is equal to 30 your what you call 2 by 3 second, and this is your D. So, D is equal to 1 upon K p, K p will be 160 upon 3. So, that is your 160 upon 3 hertz per unit megawatt, because unit also will be changed, and T p is equal to 32 by 3 second, right. Now, the load change is decreased, that is load change is negative, because it was in the problem it was 1016 megawatt, now it has decreased to 16 megawatt. So, it load change is negative, that means delta P L is minus 16 megawatt divided by the 1600 MVA base. So, that is minus 0.01 per unit megawatt. So, load has decreased, and there is a step change in a load. So, for a step decrease in load 0.0 per unit 0.01 per unit megawatt, and is a step function. So, Laplace transform of the change in load delta P L S, and here I am putting S, right, just for your understanding, will be minus 0.01 upon S, because for a step input you know if the load disturbance say delta P d, and if it is a step input then it will be delta P d upon S, and load decrease. So, minus sign. So, minus delta P g here delta P d is equal to your delta P L is equal to minus 0.01 upon S. So, from the block diagram, I mean from this block diagram, right. So, delta f is equal to minus delta PL Kp into 1 upon S plus Tp, right. So, that means I am making it one this thing for you, that delta f from this diagram is equal to minus delta PL, because delta P is 0. So, it is minus delta PL into Kp upon 1 plus STP, right. And that means, you know, in bracket if you want you can put S, right, Laplace transform, if I put what S, here also I have made it S, right, because here in the problem itself here also I have made it S, just for the purpose of your understanding. This one is S. So, this one if you put it here, then delta Fs is equal to minus of minus 0.01 upon S into your Kp upon 1 plus STP, right. Then Kp Tp value one can put. So, it will be 0.01, then Kp upon S 1 plus STP, right. So, this is the thing. That means, this is also same thing I am writing, delta Fs is equal to, that is plus 0.01 upon S into Kp upon 1 plus STP. So, it is 0.01 Kp upon 1 by 1 plus 1 upon 1 S into 1 plus STP, right. Now, this one you make it in that your this one you make it in that your what you call in two terms, right. That means, you know all these things, this thing you all this know from your calculus and other thing, that let 1 upon S into 1 plus STP is equal to A upon S plus B upon 1 plus STP. So, you have to obtain A and B, this is an identity, this is an identity. Therefore, we can write that this side I am writing left hand side first, that A into 1 plus STP plus B into S upon S into 1 plus STP is equal to this term right hand side 1 upon S into 1 plus STP. That means, A plus S into ATP plus B is equal to 1, this is an identity. So, we will compare the coefficient. So, this side if you compare that constant coefficient, so A is equal to 1, right, and there is no S coefficient here, that means it is 0. So, that means it is your ATP plus B is equal to 0. That means, if it is ATP plus B is equal to 0, that means ATP plus B is equal to 0, right, because just we are comparing this is an identity. So, Tp plus B your what you call is equal to your 0, because A is equal to 1, you put A is equal to 1 here. So, Tp plus B, so B is equal to minus Tp. That means, this expression, that is 1 upon S into 1 plus STP is equal to A is 1 upon S and B is equal to minus Tp. So, minus Tp upon 1 plus STP. So, this way first you make this you know from your what you call that second order system, right, in control system, this you are very much aware of it. So, this is like this, that means, my delta Fss will become 0.01 Kp into this thing 1 upon S minus Tp upon 1 plus STP, whatever we have got it here, right. So, delta Fs will be 0.01 Kp 1 minus S divide Tp, numerator, this one numerator and denominator, because we have to take the inverse Laplace transform. So, minus 1 upon 1 upon S plus 1 upon Tp, divide this one numerator and denominator by Tp, right. Then you take the inverse Laplace transform. If you take inverse Laplace transform, delta Ft is equal to 0.01 Kp, then 1 minus e to the power minus t upon Tp, capital Tp, right. Therefore, delta Ft is equal to, multiply this one 0.01 Kp minus 0.01 Kp e to the power minus t upon Tp, right. But Kp is equal to 1 upon d, we know this value, that is 160 by 3. So, delta Ft is equal to 0.01 160 upon 3 minus 0.01 160 upon 3 to the power minus t upon Tp is equal to 32 by 3, that we have already calculated, Tp is equal to 32 by 3, right. That means, from this equation what you can guess? From this equation you guess that for the steady state value Kp is responsible, Kp, and in this case no speed governing mechanism. So, R was not coming because delta Pg was 0, but Kp was there. But for transient, when transient response is taken, this Tp has this effect, but a steady state Tp has no effect, right. But only a steady state Kp has its effect, right. But as transient, your what you call that when t tends to infinity means this term will vanish, actually it will become 0, right. So, in that case only Kp has its effects on that steady state value, but all time constant they do not have any effect on the steady state, only during transient this has the effect, right. Therefore, this is we are substituting Kp 160 by 3 and your Tp 32 by 3. That means delta f t is equal to 1.6 upon 3 after simplification 1 minus e to the power minus 3 t upon 32. Actually, this is your response of the frequency like this. Now, at steady state, your what you call t tends to infinity, right, from this time response. So, t tends to infinity means this term is 0 because it is your minus 3 t upon 32. So, this term is vanished. So, delta f s is equal to actually 1.6 upon 3, that is 0.533 hertz, right. So, this is that because it is positive because load has decreased 16 megawatt decrease, because of negative load decrease, the frequency deviation will be steady state error will be positive. So, 0.533 hertz, that means operating system frequency will be f is equal to f 0 plus delta f s s. So, it will be 50.533 hertz, right. This is, and if you plot this graph, this is an exponential graph. If you plot this, it will move like this. From this one, it will go to your what you call to the steady state value at 0.533 hertz, right. So, you start from t is equal to 0. If you put t is equal to 0, the delta f at t is equal to 0 is 0. So, it is starting from here and exponentially increasing, finally reaching to a steady state, and this is the steady state value, that is this much, this is 0.533 hertz. This is the frequency response of this example. So, I hope you have when we will go through this video, I hope you will be understanding this, right. So, things are simple. Now, with controller, just see with controller here, if controller is there, we cannot put that t tends to infinity or s is equal to 0, we cannot do that. Here we have taken only integral controller. A proportional integral can be considered, then proportional integral derivative can be considered, all sort of controllers can be tried, but for the classroom exercise we have just taken that minus k I upon s, k I is the integral gain setting, and this we have taken, right. So, only integral controller we have taken. So, in this case, your what you call that if you take for this system, if you take for example, that is minus k I upon s we have taken, that if k I is, in this case k I will be positive, if you take minus k I upon s, if you take only k I upon s, then k I should be negative, but I have taken minus k I upon, otherwise what will happen, system will become unstable, right. So, that is why minus k I upon s means k I will take positive value. Now, for this system a controller is there. So, we here we cannot get any steady state block diagram because of this s. If we can put s is equal to 0, but here we cannot do that. So, we will go for final value theorem with controller, right. So, it is isolated power system with integral controller, and this is your what you call, we will see the steady state value, that when you put integral controller you will find the steady state value delta f s s will become 0, whereas delta and with this controller at that time delta p g s s will be exactly delta p l. It will because frequency at that time there is no frequency error, delta f s is 0. So, that means d into delta f s s term was there, but in that case that the difference was coming because of the steady state error in frequency, but in this case when delta f s s will become 0. So, d into whatever delta f s is 0. So, that term will not be there, and because of this controller action delta p g will become delta p l. Now, look how to do it, final value theorem. So, in this case first you write down that equation delta f is equal to k p upon 1 plus s t p, right. This is known. Then your this is actually this is known. Then what you will do that delta p g is equal to b. I have written your few one or two step ahead, but I am telling you how to make it, right. I will write little bit slowly here, right, such that things will be this thing. Look at this diagram, look at this diagram, right. This, that means this is delta f, this is delta f, that means here also it is your delta f, right. Here also I have written delta f, that means your delta p g is equal to your minus k I upon s into delta f minus 1 upon r into delta f. So, delta f is common. So, that means delta p g, right, is equal to, that means this delta p g multiplied by all these things will come, right. So, it will be your minus delta f, right, minus delta f, that means your if you take minus delta f upon r minus k I upon s. So, delta f will be common, and then your in bracket it will be 1 upon k I plus your 1 upon r, right. Let me put it little bit this thing, right, minus 1 upon k I plus 1 upon r, right, into this all this term into all this term, that means into 1 upon 1 plus S T G into 1 upon 1 plus S T T, right, into your 1 upon your 1 plus S K R T R, right, divided by 1 plus S T R. So, all this term will be coming delta P G is equal to, that is why whatever we are writing here. So, this delta F actually delta P G minus delta P L into K P upon 1 plus S T P. So, delta P G, right, delta P G is equal to your delta F is equal to your delta F is equal to your K P upon 1 plus S T P from this diagram, K P upon 1 plus S T P into delta P G minus delta P L. This delta P G, whatever it is written here, this delta P G you substitute here, right. So, if you do so, that is why you are writing that K P upon 1 plus S T P, this whole term actually this term it is delta P G. Just now we have written that this term is delta P G, right, this term is delta P G. So, all these terms are written here minus delta P L, this term is delta P G minus here it is delta P L, right. If you simplify this, that means this one if you want to write, right, I mean after simplification. So, this is your delta F is equal to. So, what you can do is that this this term, all these things 1 plus K P into, if you multiply this thing, it will be K P into K I upon S plus 1 upon R, then this side it has come, because when you multiply all this term, this delta F term is there, with this delta F term is there. So, this term multiplied this term into this thing will come to the left hand side, right, then minus K P into delta P L 1 plus S T P. I mean if you make it like this, that this is your delta F is equal to this one, and this term with this term from, I mean from here to here with this term delta F is associated with that, multiplied by your what you call K P upon 1 plus S T P. So, what you do, you multiply this, right, you multiply this, then you bring this term to the your what you call to the left hand side, just writing 1 or 2 lines for you, such that because here it will consume some time for writing this one, but it is understandable. Look at this term, So, in this case what you can do is that delta F you multiply all these things, it will become your K P upon 1 plus S T P, a minus sign because of this one, into K I upon S plus 1 upon R, right, into your 1 plus S K R T R divided by, right, all the terms 1 plus S T G, 1 plus S T T, 1 plus your what you call S T R, right, into this delta F term is there, into delta F, right, then minus your delta P L into K P divided by 1 plus S T P. This term you bring it to the left hand side, this is delta F, this is delta, bring it to the left hand side and take delta F common. If you do so, and little bit you simplify, if you do so, you will get this 1 plus K P into all this term into delta F is equal to minus K P into delta P L upon 1 plus S T P, that is whatever I have just written, minus delta P L into K P upon 1 plus S T P, right. So, if you bring to this side and then your after this little bit you simplify, it will be R K I plus S upon S R. So, S R is here, right, and R K I plus S R is here, and this is 1 plus into everything is there, delta F is equal to minus K P into delta P L upon 1 plus S T P, right. Next is, so next one is, let there is a step load change in delta P D. If there is a step load change, the final value theorem we want to apply. So, delta P L will be delta P D upon S. This delta step load change I have said, no question of increase or decrease, according to the increase it will be plus, according to the decrease it will be minus. So, in general delta P L will be delta P D upon S for a step load disturbance, right. That means for a step load disturbance in this equation delta PL you put delta PD upon S here, delta PD upon S. If you do so, then it is becoming actually, if you put delta PD upon S, then delta PD upon S you put it here and multiply both side by S, right. So, first you put delta PD upon S in this equation, delta PL is equal to delta PD upon S, you put it here and both side you multiply by S. If you do so, that is why here it is 1, if you both side multiply by S. So, if it is delta PD upon S, this S will be cancelled, it will be S plus S into something. So, that is why it will be S, and this S if you multiply both side, that S will be cancelled here, you multiply, this is actually, this term will be delta PD upon S. So, multiply both side by S. So, this denominator S will be cancelled, it will be minus Kp into delta PD upon 1 plus STP, and this side if you multiply by S, it will be S plus this 1 S is here. So, S will be cancelled, it will be Kp into this thing, R into all this thing. So, whatever we are doing is same thing we are getting. So, not writing here, I think you can do it yourself, just a simple thing, put delta PD upon S, then multiply both side by S. So, you will get this expression, right. That means your S into delta F, you simplify this one, that S into delta F is equal to your whatever things coming, right. So, is equal to minus Kp, then delta PD into R, all these things. I mean, what will happen actually, if you make it like this, it will be it will become S, look at the new denominator, it will be SR into all these things, SR into all these things plus, this is a plus sign, there is a plus sign here, plus Kp into RKI plus S into this term, right. And then this one your what you call minus Kp into delta PD into R 1 plus STG 1 plus STT 1 plus STR into S. That means, both sides what we are doing is actually we are multiplying by S, both side we are here it is S, here also it is S. So, both side we are trying to multiply by S. So, that is why this side when you multiply, that minus Kp into delta PD is there, along with that this side will multiply R into all these things divided by this thing, then both side you please multiply by S, that means S del F. So, delta F is limit S tends to 0, S delta F, right, and as S tends to 0 means it is 0. So, steady state error of the frequency will be 0. So, thank you very much. I think you have understood this, little bit you do it and multiply both sides. So, it is SS. From control system you have studied all this. So, thank you, we will be coming.